Hello, welcome back to the course on Polymeric Biomaterials. We are still looking at structure property relationships, and in today's lecture we will be focusing on chain conformation and structural characteristics. Now, in the last lecture we were broadly looking at molar mass and we were trying to connect it to the degree of polymerization or the average number of mers in the chain, and we looked at some average properties for a number of chains. We looked at distributions. There the question we were asking was, what is the size of these chains? Now, in this lecture we will ask that same question but from a slightly different perspective. In the previous lecture we were interested in just the chain length, distribution of chain lengths, the relative contributions of the different weight fractions to the overall molar mass and so on. In this lecture we are going to ask, how do these chains orient themselves in three-dimensional space, for which we will have to look at something called chain conformations. So, here the focus of this lecture will be looking at a single macromolecular chain, but then asking how do conformations result in different sizes in 3D for a polymer. And to understand that, the starting point for us will be what you will call an ideal chain with its own set of assumptions, which is one of the simplest ways to think about these chains. And then we can add realistic constraints to a model that can describe the ideal chain, and then we can try to see how the sizes can change in 3D. And we will also look at a few different structural characteristics, numbers essentially, that can be used to quantify these sizes, such as end-to-end distance, persistence length, radius of gyration and hydrodynamic radius. And then ultimately, as always, we will connect how these single chain properties or characteristics can be connected to bulk properties. Now, the philosophy with this lecture is to have a good physical understanding of all these structural characteristics. Our goal is not to derive from scratch each of these formulae, etc. What we will do primarily is focus on understanding from a physical perspective, from a conceptual perspective, the size of a macromolecule from a single chain perspective. Later, I will also provide a reference in case you are interested in looking at detailed derivations for some of these things. So, we will start with that question first, which is, how big is a macromolecule or a polymer really in 3D? Now, for that we will start with our familiar example of polyethylene of say molar mass 280,000 gram per mole. On the left side you have ethylene, which is simply 28 gram per mole, and let us assume N is 10,000. This will lead to polyethylene of molecular weight 280,000 gram per mole. And can you try and speculate how many carbon-carbon bonds will be there in this molecule? If you have guessed it right, this should contain 20,000 carbon-carbon bonds in the backbone. Now, if you start with this as an example, we will now consider two extreme length scales here in 3D. One is, this chain can be thought of in one extreme as fully stretched out and perfectly linear from end to end. That would be what we would call the contour length, which is this chain fully stretched out from end to end. The other extreme is, the chain is completely collapsed and forms a dense globule, where you can now approximate it as a sphere and you can talk about an equivalent sphere radius. So, these would be considered the two extremes for this. Now, let us dig a little bit deeper and ask, can we come up with some numbers, some quantities that can describe both contour length and this sphere radius and try to understand what the differences in these extremities are. So, we will first begin with looking at the linear or the fully extended chain. Now, there is an easy way for us to approximate the size of this based on the length of the carbon-carbon bond. So, if you approximate the carbon-carbon bond length as being roughly about 0.15 nanometers, which is an approximation, and if you consider for the example given earlier with 20,000 cc bonds, then the contour length from one end of the polymer to the other end in the fully extended stretched chain state would be 20,000 times 0.15 nanometers, which will roughly be about 3 microns. And to get a sense of what 3 microns is you simply have to consider the fact that a cell is about, a small cell would be about 2 times that size. A red blood cell, for example, will be about 5 to 6 microns. So, this length scale we are getting, this 3 micron length scale is about half that size. So, same order of magnitude. While this might seem like an approximation that we are doing, it is a very useful exercise that we will often do not just in this course, but in engineering in general, which is order of magnitude estimates. Where you are not so interested in the details of the calculations, but you are interested in understanding the physical significance of numbers or to get an idea of where you lie on that spectrum. The details are very important when you solve problems or when you are designing something, but for a conceptual understanding, it is oftentimes the order of magnitude estimate that will really help you get a good sense of the physical significance of the numbers you are dealing with. So, that is sort of what we are trying to do here. So, note down this length scale here for the contour length. The other extreme is for the sphere or the dense globule, right. Now, if you approximate that shape as a sphere, one can think of a length scale associated with it as being equivalent to a sphere radius. And to get radius, you will have to get that from volume, and for volume you will have to rely upon mass and density. So, again we will do that same thing that we did earlier for the fully extended chain, which is to do back of the envelope calculations to get a sense of the order of magnitude of what we are dealing with here. So, if you assume that the bulk density of bulk polyethylene is about 0.9 gram per cc, which is again an approximation, and note that that number will change depending on what type of polyethylene you are dealing with. But you can use that as a starting point for this discussion. Then the volume can simply be calculated based on mass over density and accounting for the Avogadro number. So, you will roughly end up getting about 516 to 520 nanometer cube volume for that same chain as the fully extended chain. And if you calculate the equivalent sphere radius for that volume, you will end up with 5 nanometers. Note that for the same chain that we saw here, which is the linear fully extended chain, that exact same chain in the sphere or the dense globule form is giving you a length scale that is 3 orders of magnitude smaller than the contour length. Now, to get a sense of what that means is, if you consider the equivalent sphere radius 5 nanometers as equal to the size of a let us say a basketball, whose diameter will roughly be about 10 inches, let us say. If that is the length scale you are talking about here for the dense globule, you are talking about 10,000 inches here for the linear fully extended chain, which would be approximately the length of a basketball court. So, for the same chain, in one state, in the fully extended state, you are talking about the length scale that is of the order of a basketball court. In the other case, for the same chain, when it is in the dense globule state, we are talking about a length scale that is of the order of, say, the size of a basketball itself. So, these are two very, very extreme cases for the same chain. Now, what explains these differences? How do we come to terms with these very large differences in length scales for the same chain itself? That can be explained based on conformations that these chains can take. Firstly, we note that we are using the word conformations here, and we have earlier seen the word configuration. Note that this is not the same as conformation. Configuration is something that cannot be changed after synthesis. It is fixed during synthesis, and the only way to change configuration of a polymer molecule is to break primary bonds and reform them, which is not easy at all. So, do not confuse that with conformations here, where it is reasonably relatively easy to change conformations of these kinds of systems based on rotations around carbon-carbon single bonds, for example, as we saw in the case of polyethylene here. So, throughout the chain, every CC bond, especially given the fact that the bond is a single bond, it can rotate and take on multiple angles, and that rotation leads to differences in how the side groups interact with each other across the carbon atoms, as we will look at very shortly. So, right away you see that we are using words like dihedral angle, bond angle, etc., and so some terms need to be defined before we proceed further, and we will use this example here to define these terms more clearly. So, shown here is a cartoon or a schematic representation of a 4-carbon segment of a polyethylene molecule. Now, obviously the polyethylene molecule is much longer than this, and it is going to proceed in both directions, and we are looking only at 4 of those carbons here to get a good understanding of what dihedral angles or torsional angles are and what bond angles are. And these carbon atoms are labeled Ci-2, Ci-1, Ci and Ci+1. So, those are the 4 carbon atoms. Now, as you can readily appreciate, between 4 carbon atoms we can define 3 bonds, and those bonds have their own bond vectors associated with them, namely Ri-1, Ri and Ri+1. So, we have 4 carbon atoms, we have 3 bonds that we have defined between them, each associated with their own bond vectors. So, the carbon atoms and the bond vectors should be clear. Now, we have 2 angles that we are talking about here. One is theta, which here we are defining as the angle between 2 bond vectors. Now, if you look up some textbooks, you might also have seen that theta sometimes is also defined as the bond angle itself, wherein for this kind of a system, for a carbon-carbon single bond, that would roughly be 109.5 degrees. But the way we are defining theta is not this. Here what we are doing is, if this bond vector were to continue this way, were projected that way, theta is defined as the angle between the bond vector here and the bond vector here. Now, you can easily see that the way we are defining theta here, which is the angle between 2 bond vectors, will simply be 180 minus the bond angle as classically defined, which is 109.5. So, if you subtract it, you will roughly get about 70.5 degrees or 70 degrees roughly for the way we are defining theta here for this system. So, that is an important distinction to keep in mind. The other angle that we are defining here is the dihedral or the torsional angle. Dihedral angles are typically defined between 2 planes, and here we have 2 planes formed by the bonds bonds represented by the bond vectors Ri minus 1 and Ri and Ri plus 1. So, you have two planes that intersect, and the angle formed between them where the carbon can rotate is the dihedral angle as shown here. So, as you can clearly see, theta which is the angle between the bond vectors and the dihedral or the torsional angles are not the same. In fact, for a fixed value of theta, you can have the dihedral angle go anywhere from 0 to 360, all the while theta being fixed. Right? And although that is true, the fact that the dihedral angle can go anywhere from 0 to 360, there are specific angles there that are of interest to us from a steric hindrance perspective, which we will look at. So, shown here are two different ways in which the CC bond has rotated, resulting in at least two different ways along the potential energy diagram, where you have what we call the trans state and the gauche plus state, and depending on the angle of rotation, the gauche itself can produce two states, namely gauche plus and gauche minus. And just as an example, we are looking at trans and gauche plus here. So, first of all, we note that both of these are representations of different conformations for this system here, and these depend both upon the thermal energy available to the molecule based on temperature, as well as the relative steric hindrance that the atoms will face when they are either in the trans state or in the gauche state. The trans state represents a global minimum in the potential energy diagram, where you have the lowest steric hindrance, because the hydrogens along the carbon, if you look through the bond, the hydrogens are pointing in opposite directions, or in other words, these two bonds are what we would call collinear, resulting in least steric hindrance among all the conformations possible. The gauche state is also a staggered state, but is a higher energy state than the trans state, because there is some level of steric hindrance as compared to the trans state among the atoms attached along the carbons, as shown in this diagram here. Now, for a polyethylene molecule, it may be hard for you to appreciate exactly what is going on here. So, just for understanding this a bit better, we will look at the example of another 4 carbon molecule that you are probably familiar with, which is butane, and shown here are what are called Newman projections, which would give you a much better idea of what we are talking about in terms of potential energy diagrams and relative conformations. So, again you see here we are looking at the dihedral or the torsional angle on the x axis and then potential energy on the y axis. So, higher up the state is, the less favorable, energetically favorable it is, and you notice that the T or the trans state represents the global minimum, and what we are shown here is we are looking through the bonds along the carbon-carbon backbone, and what you see in the trans state is it is a fully staggered state, sometimes also called an anti-state, where there is absolutely no hindrance for you to see the atoms attached to the other carbon when you see from this side. So, it is in the fully staggered state where there is no overlap of the electron clouds, which means that this state is going to be the lowest energy state among all the states possible. Now, compare that with the two gauche states. If I rotate this bond 120 degrees this way or that way, you can see that CH3 has moved this way or that way, and compared to the trans state, this will have a slightly higher energy state because of slightly higher steric hindrance due to the position of the atoms along the carbons. Of course, they are still much better than the states represented by these or these, where those will represent eclipsed, what you would call eclipse states. And even here there is a subtle difference. In these states, energy is even more higher, probably the highest among all of them, because there is a direct over the CH3s will directly be behind one another. So, when you look through one methyl, the other methyl will not be visible because it is right behind it, and that leads to the maximum steric hindrance, leading to the highest energy state, as opposed to these ones where it is a CH3 hydrogen kind of an eclipse. So, slightly lower energy compared to the CH3 eclipse, but again these states, because they are higher energy, will not be favored easily from a steric hindrance perspective. Now, which state or which conformation a carbon-carbon bond wants to be in will, like I said earlier, depend upon the thermal energy present. If there is sufficient thermal energy for them to move across states, they will move so. So, you can immediately appreciate that in the melt state, these conformations where the temperature is quite high, these conformations will be enabled, or even the transitions. And if you want to get a sense of the ratio of the states for the gauche versus the trans, that is shown by this formula here, and you can readily appreciate that this 2 is simply coming from the fact that you have 2 gauche states as compared to 1 trans state, and delta E is simply the energy barrier between the trans and the gauche states. Now, this should give you a good sense of a single carbon-carbon bond rotation when you think about what conformations can be favored, what conformations are less energetically favored, and how those can in turn depend on temperature. Now, you can extend this argument to the entire polyethylene molecule, where each carbon-carbon bond has the option to do this. And you might pause here and think about, will all possible conformations be favored for all the carbon-carbon bonds equally? If your intuition is right, you will immediately see that that will not be true. Now, for a chain with 20,000 bonds, as we saw, at every carbon-carbon bond step, that has the possibility for 3 different conformations, resulting in 3 to the 20,000 possible conformations. Now, if you think of this molecule sampling or changing as a thought exercise, changing conformations every 1 picosecond, let us say, you will be shocked at how long it will take for it to sample all the conformations. It will be much larger than the age of the universe itself. So, that should also tell you why the probability of the fully extended all trans state, where everything is fully stretched out, or the zigzag state, is 1 in 10 to the 10,000. What you can also now start to think about is, because all of these states are not energetically the same, depending on energy barriers across states, and depending on which state is energetically more favorable under a given set of conditions, based on what is the temperature, what are the solvents, you get different kinds of conformations that are promoted. Now, one thing to note here is, which we will look at in more detail later in this lecture, is to understand that conformation and chain flexibility are related. In other words, the all trans fully extended state is considered the rod-like state, which is considered stiff compared to the introduction of the gauche states, which introduces flexibility. That is an important point to keep in mind as we go through this lecture because here we are now connecting conformation to words like flexibility and rod like rigidity. So, the association is important here. Also note, can you speculate on the presence of say double or triple bonds or the presence of bulky groups along the backbone, or if you have high energy barriers, what that would do to conformations? You can immediately see that these things will restrict the bond rotation and will change the way the polymer conformations can happen. While we are focused here primarily so far on the CC bond, it is important to keep in mind that when you have double bonds or when you have bulky groups in the backbone or on the side, those things can restrict chain rotation. Now, as you can now clearly start to think about different conformations, a large number of different sequences of T the trans, G plus the gauche plus and G minus the gauche minus can cause the chain to wander about in space, wherein the typical size that you can think of for this chain or macromolecule will be intermediate between the fully extended chain and the dense sphere. The fully extended chain, for example, the all trans zigzag state occurs with very low probability as we saw, and the dense globule also has a low probability. Because of multiple conformations that can be introduced in each of these bonds, that all trans going from the all trans to some flexibility is achieved through the introduction of several gauche in between, and that is also a function of temperature. If you have the melt state, if you are increasing the temperature, you can now start to think about more gauche states being favored, and it is a bit counterintuitive because with increase in temperature you start to think that everything increases. So, you would think this becomes longer. Actually the opposite happens, where with increases in temperature more gauche states are favored, so chain starts to become more flexible and the overall size starts to go down. That is a very interesting aspect in polymers. So, if you now consider just 3 different temporal snapshots of the same polymer chain. So, structurally the same polymer, same chemistry, 3 different conformations based on how each carbon-carbon bond decides to take up different conformations. So, what I am showing here is a temporal snapshot going from left to right. At one time instant it could take up this conformation, at another time instant it could take up this conformation, at another time instant it could take up this. So, as you can clearly see, within energetic constraints you can have billions and billions of conformations. So, it is very difficult to talk about instantaneous conformations, rather we are now interested in averages, for which we will have to now think about the polymer as a random coil. And this is why, if you remember, we have talked about the cooked spaghetti analogy for polymers, which is a random entangled mass of chains. A random coil, to note, does not refer to a specific conformation, but is actually a dynamic and flexible conformation that represents a statistical distribution of shapes as a function of both temperature and solvent. So, if you think about that same chain now, if you zoom out a bit and do not focus so much on the links, but look at the chain as a whole, in one instance it could look like this, in another instance it could look like this, in a third instance it could look like this. These are all what we would consider random coils, which would again be, remember that they would be dynamic and flexible, they are continuously changing because of the solvent and the temperature. Now, we first want to ask, how do we understand in terms of sizes, how do we want to understand conformations of the random coil itself and the overall chain. For us to look at this in more detail, we have to first define what you will call an ideal chain, from which or based on which we will develop models to understand what we can think of as an average size of this chain. Now, when you hear the word ideal chain, you might be familiar very likely with ideal gases, where ideal gases assume no interactions between the molecules. So, these would be molecules for ideal gases. So, like ideal gases, here there are no interactions between the monomers for an ideal chain. Another very important idea for ideal chains is ideal chains do not assume excluded volume. So, excluded volume effects are ignored. We will look at this in more detail as we go through in a later topic what this means, but for now one way to understand what excluded volume is when polymers keep doing this dynamic fluctuation and so on, because these molecules occupy volume, you can't have chains cross path or go through or intersect, or no two polymeric segments can occupy the same point in space, in 3-dimensional space. So, the effective size that you get for a real chain will be larger than for an ideal chain, which does not take into account these excluded volume effects. So, in an ideal chain, chains can actually cross over, right? Chains can intersect, chains can go on top, they can do all kinds of things which would be considered unphysical. Is that still okay? As it turns out, it is a great starting point for us to understand how chains behave eventually, because we can now start to think about, just as we do with ideal gases, we can now start to think about, if this is the model for an ideal chain, can we now start imposing constraints based on realistic considerations, and then start to ask what are the deviations from ideal chain behavior. That is one way to think about this. And one of the simplest models we will look at for this is called the freely jointed chain model. Any model that you come across, the word model itself simply indicates that the framework that we are going to come up with is going to reflect some aspect physically of the system, likely through a mathematical equation. And all models will have a set of assumptions, and when those assumptions get violated, the model becomes limited. The model becomes no longer applicable. So, it is very important when we start looking at models to know what the assumptions or the underlying framework is for the model. This model, like I said, is the simplest model for an ideal chain. It considers n rigid links, which would be the bonds between the covalent bonds between the mers, each with a fixed length of L, and L here is a vector. One very important point to note here is the orientation of one link does not affect the next. This is what we would call uncorrelated. What that means is, the first link that goes and the next link that comes need not have any connection at all, in the sense the direction in which the first link points and the direction in which the second link points may have no correlation. Does that really happen in a polymer? No, but this is the assumption of the ideal chain or the freely jointed chain model. The other assumption we make here is no restrictions either on the bond angles or on the dihedral angles. Again, if you notice here, bond angles typically for carbon-carbon, the tetrahedral angle is typically fixed at 109.5. Again, you can try and understand how that relates to what we defined as theta as the angle between two bond vectors on an earlier slide. In any case, For a carbon-carbon bond, single bond, this would be the tetrahedral angle, but you notice here clearly that this model assumes no restrictions on bond angles. Now, given that these are the assumptions that you have for the freely jointed chain for an ideal chain model, you can now define something called an instantaneous end-to-end vector, which is simply the straight line vector between the first and the last mer in the chain. And as an example, we will consider just two conformations. So, you have L, 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 L and so on, where link 1, link 2, 4, 5. For n such links where all L's are the same, the subscripts simply indicate the number there. Between L1 and Ln, you can draw the straight line vector, which is just the instantaneous end-to-end vector. And what you are asking here is, what is the straight line vector? What is that distance between that first mer and the last mer in 3D? Now, you can have another conformation for which the instantaneous end-to-end vector could be smaller or larger depending on the conformation and depending on the separation of the first and the last mer. So, you see very quickly that as we saw earlier as well, instantaneous properties are not very useful. Although they are useful as a starting point, they are not of any practical use for us. So, as we have seen, the instantaneous end-to-end vector is not a very useful quantity to look at because the conformations keep changing continuously. The polymers are, the chains are very dynamic and continuously changing conformations. So, what might be more useful to talk about instead of an instantaneous end-to-end vector is an average end-to-end vector. And idea here is determining the instantaneous conformation is neither possible nor useful. What makes more sense to talk about is an average end-to-end vector. And here you notice we have introduced two new things here. One is we have called it an ensemble average. The other is we have also introduced these angular brackets here. So, we will take a minute to look at what that is. Averages can be broadly taken in two ways. You can take a chain and keep following it over time. Over time, this is the conformational changes that the chain makes, and you can follow a single chain like this over time and take the average. That is one way to do it. You can also take a snapshot of lots of different chains, a single snapshot, and all these chains will be structurally identical, but they will exist in different what we would call microstates. And then you can average over all of them, and such an average is called an ensemble average, where you are taking a single snapshot at a certain point, for example, of lots of different chains, and you are asking what is the average conformation here. The other thing we have done here is to introduce these angular brackets, like I said, that simply indicates an ensemble average. So, you are looking at an ensemble average end-to-end vector. Now, it turns out that the ensemble average end-to-end vector, when you access it directly for a random coil conformation, will be 0, because all the conformations are equally likely for the different chains are equally likely to point in all directions with no bias or preference for a specific direction, which means if you take the average of all of them, the net will go to 0. And one way to sort of physically understand that or contextualize that is to realize when you have if you have taken any course on statistics, for example, and you start looking at accessing standard deviation, if you try to directly access standard deviation, you will realize that the value will always be 0, which is why you first do what is called a sum of squared deviations, determine the variance, and you take the square root to calculate standard deviation. So, likewise here, note that while the ensemble average end-to-end vector itself, when you access it, is 0, the average end-to-end distance itself is not 0 and it depends on L and N. And like I said, for that you will have to resort to what we would call a root mean square value, where you take the average of the squared values and take the square root of it. And just as I talked about in the analogy, if you calculate standard deviation directly, what you would do is, because standard deviation is simply the average deviation of the data points from the mean, and the way the mean is determined, you would likely have an equal quantum of deviations in the positive and negative directions. So, if you take the sum of those deviations, they will always go to 0. So, the typical approach used in statistics is to calculate what we would call, of course, this is for a population, what we would call sum of squared deviations. So, you take the deviations, you square them, that gets rid of all the negative values. So, you end up getting something called variance, and the square root of that, when you take that, will be standard deviation. So, if you can appreciate this analogy or this example, what you will immediately see is that while the ensemble average end-to-end vector itself is 0, if you take the root mean square value, or if you square the values, take the average and then take the square root, that number itself will not be 0, and that will give you a physically meaningful number. If you end up doing that, what you will end up getting is this expression here. So, you see here, this term simply means its root mean square. So, all those terms are embedded in that one symbol itself, right. So, its root mean square end-to-end distance is given as n to the half times L, or if you now want to think about size, as we said earlier, the size or the end-to-end distance, root mean square end-to-end distance scales as n to the half. This quantity simply, this tilde symbol simply means that it scales as n to the half, and when we say scales, we are interested in these scaling exponents. So, here we can talk about a 0.5 scaling exponent, and contrast that now with the fully extended contour length that we saw earlier, where the scaling is n to the 1, and here you notice it is n to the 0.5. So, for an ideal chain, the scaling for root mean square end-to-end distance with n is 0.5. What is interesting here to note is that, as the name indicates, this is simply the ideal chain, and this freely jointed chain model does not account for any realistic constraints. So, using that as a starting point, we can now start to incorporate other constraints, more realistic constraints, which will actually end up leading to a higher root mean square end-to-end distance compared to the freely jointed chain model. And just as one example, we will see this freely rotating chain model, where the bond lengths are fixed and the bond angles are also fixed here, and the dihedral angles are free to rotate. And here you can ask, unlike the freely jointed chain model, here you can ask, can you determine the correlation among bond vectors of the chain, or in other words, each subsequent link has some preference for heading in the same direction as the previous link. So, if you now consider these aspects and you look at the final expression for mean square end-to-end distance, you see that the bond angle is embedded here. And just as an example, if you try and substitute theta is equal to 70, you will see that the factor here will be about 2. and that 70 comes from how we defined theta earlier. For the 109.5 or roughly thereabouts bond angle, 180 minus that will be theta the way we defined it, and if you substitute that here, you will end up with a factor of 2, which is roughly twice the mean square, not root mean square, the mean square is 2 times that predicted by the freely jointed chain model. But note here that the root mean square scaling is still n to the half here. Now, there are more models that you can think about which include more and more constraints. We can also look at the scaling from a solution perspective, where now you see that we are talking about expanded real chains as opposed to ideal chains. If you take the most general case of the root mean square end-to-end distance as scaling with n raised to nu, which is the scaling exponent, you can actually show that in what we call a good solvent, you get the expanded real chain where the size is larger because the scaling exponent will be about 0.6. And then you have a poor solvent for which the chain will get collapsed. In a good solvent, the polymer solvent interactions are favored compared to polymer-polymer interactions. So, the chain wants to expand, and that is why it is called an expanded or an extended real chain, where it is called real because excluded volume effects are accounted for, where you can't have unphysical things like chains crossing each other or intersecting into each other, etc. In a poor solvent, the chains want to interact with each other because polymer-polymer interactions are much more favorable than polymer-solvent interactions. So, the polymer wants to sort of expel the solvent and wants to stay close to itself, which would lead to what we would call a collapsed chain. And there you see the scaling is about 0.33. And in between you have the ideal chain which we just saw, where the scaling is 0.5. And one way to realize the ideal chain condition experimentally is to use something called a theta solvent, where the solvent is just poor enough to exactly counteract the extruded volume effects, and that also occurs at a specific temperature called the theta temperature. So, you see we are talking about solvent effects and temperature effects under a broad umbrella, and as we will see later under a separate theme, temperature and solvent effects are very unique and very special for polymers. So, we will look at these effects in far more detail in later lectures, but for now it is important to understand that what we are interested here is to look at size using such scaling laws for mean square, root mean square end-to-end distance, where based on the exponent you can now predict whether the solvent is a good solvent or a theta solvent or a poor solvent, based on whether the chains want to be in an expanded state, which are real chains, or a collapsed state, or the ideal chain condition which is achieved when you have a theta solvent at the theta temperature. Here it would be good for you to now pause and look up something called a coil globule transition. Now, we have looked at coils, we have also alluded to the idea of globules. This happens to be a very important conformational change that occurs in proteins and can explain some aspects of protein folding and denaturation. Now that we have looked at end-to-end distance or root mean square end-to-end distance and how to think about size using that and the scaling exponents, we can now focus on another aspect related to rigidity and flexibility of polymers based on different conformations. And here we will look at another associated characteristic of the structure of a chain called persistence length. So, couple of points to note before we look at persistence length in itself. First point to note is the maximum end-to-end root mean square end-to-end distance is achieved only if all the angles, all the dihedral or torsional angles are in the trans state, leading to a rod-like zigzag conformation, right, which should represent a very stiff kind of a chain. That is why it is called a rod-like conformation. But note that many polymers do not have all C single bond C. You can have C carbon with a benzyl ring in the backbone. You can have inorganic polymers as we saw, it does not have to be a C bond itself. You can also have unsaturated bonds, which will all make it difficult for the backbone to continue in one direction, as the bulkier groups will restrict rotation due to steric hindrance. So, you can have a combination depending upon which ones are trans, which ones are gauche, etc., depending on how easily the rotation is favored, and of course based on temperature and solvent effects. Now, one very important or very popular model for describing what we would call semi-flexible chains is this model called the worm-like chain model, which is a special case of the freely rotating chain model that we saw earlier, except that the bond angles are very, very small here. Now, this is one model that can describe both flexible and semi-flexible chains, where depending on the length scale of interest, you can get either the chains to be stiff or chains to be flexible. For example, stiff over short distances and flexible over longer distances. And as an example, you can have large side groups inducing helical conformation and stiffness, hindering the ease of these TG transitions, for example in double stranded DNA, which would be considered a stiff macromolecule. Now, what determines this, whether the chain is stiff or flexible, I said depends on the length scale of interest. So, now we can talk about a standard length scale, and in comparison to that we can ask, is the length scale of interest larger than that or smaller than that, and it turns out that can be used to define whether you are talking about stiff or flexible chains. Now, one way to think about this is, you might have all seen a garden hose that you use at home, and a garden hose will look typically like this. Now, you take 2-inch piece of the garden hose and you compare that with, let us say, a 50-foot long garden hose. Can you try and figure out which would be considered stiff and which would be considered more flexible, which would be considered rod-like and which would be considered coil-like? So, you can immediately see that the short 2-inch piece would be considered much stiffer compared to the long flexible 50-foot pipe. So, if you keep that analogy in mind, understanding persistence length will become much easier, because persistence length L sub p quantifies bending stiffness. And you are asking a very simple question here in terms of moving along the backbone. If you go along the chain in the backbone, how far do you have to travel before the orientation changes appreciably? In other words, over what distance do the bond vector correlations that we saw earlier persist? And that can be used to define persistence length, which tells you something about stiffness. And for semi-flexible chains, persistence length can be thought of as a structural parameter that defines this rod, which is very stiff, to coil crossover. So, the same worm-like chain model can now be used to describe the properties of semi-flexible polymers which can exhibit rigid or flexible behavior depending on the length scale of interest, and that length scale of interest can be thought of in relation now to persistence length. So, just as an example, we will look at the two extremes for you to get a quick sense of how this works. Just as we saw the 2-inch piece of the garden hose and the 50-foot length of the garden hose, you can now consider two extremes. Now, if the length scale of interest, that is your chain length, is much smaller than the persistence length, the scaling happens to be, the scaling for the root mean square end to end distance happens to be n, which is like the rigid rod in the contour length limit. If your chain length or your length of interest is much larger than your persistence length, then the scaling for the root mean square end to end distance happens to be n to the half, which would be the limit for a flexible coil or the ideal chain limit. Now, these represent the two extremes. Can you now see how to contextualize this in the garden hose example that we just saw? You can try and do it as an exercise and see in which case would you consider that to be the rigid rod, and in which case would you consider it to be a flexible coil as we have described here. Now, this is important for two reasons. One is we have been able to talk about rigidity or flexibility of the chain of a single chain based on the parameter called persistence length. So, that helps us, it is a structural parameter that tells us something about the rigidity of the chain. More importantly, we have now been able to relate root mean square end to end distance, which we have seen earlier, to the different extremes going from the rod to the coil through a transition. The transition is simply where L is of a comparable length scale as the persistence length. So, the worm like chain model describes this entire continuum going from rod to coil. So, the second point that I was trying to make is you have now been able to connect root mean square end to end distance based on the scaling for the two extremes and anything in between. And as an example, the persistence length of DNA is of the order of 50 to 60 nanometers in 0.2 molar NaCl. Now, what is interesting about DNA is you can have different persistent lengths based on the salt concentrations. You can change the salt concentration and change the persistence length. So, for low salt concentrations where the charges on the DNA repel each other, DNA can be very stiff, the molecule itself can be very stiff. And as you increase the salt concentration, for example, those charges get screened and DNA can become more flexible. So, this is one way, by changing the salt concentration or the pH, one can change some of these structural properties. Another important structural characteristic that we will look at, in fact, two structural characteristics we will look at are radius of gyration and hydrodynamic radius. Now, why do we need these in the first place? For that, we will have to first understand what the limitations are with the root mean square end to end distance that we have just seen. Firstly, it is not a very easily experimentally accessible quantity. And what is important here is the root mean square end to end distance also pays particular attention to the start and the end monomers. While for a chain, all monomers are important, whereas it somehow seems to pay very special attention to the starting and the ending mers. And as you could have correctly guessed by now, the root mean square end to end distance works very well primarily for linear long polymers. But if you have branches where you have many dangling ends, or you have rings where there are no ends, or if you have dendrimer like structures which are more complex molecules where you can't think of one end to another in the classical sense, defining a root mean square end-to-end distance becomes very complicated. So, we now have to come up with other structural features that can help us define the size of a macromolecule in 3D without specific constraints of it has to be linear, it shouldn't have branches, etc. And that is where these two radii help us. One is the radius of gyration, the other is the hydrodynamic radius. Radius of gyration is the average square distance between the mers in any given conformation and the polymer's center of mass. So, it is the average square distance between the mers in a given conformation and the polymer's center of mass. So, it gives you some sense about the spatial distribution of masses within a macromolecule. Another more intuitive way to define radius of gyration is to think about it as an average distance between all pairs of monomers in 3D, and that would be given by this formula where Ri and Rj refer to the bond vectors for any two of those monomers. So, if you think of radius of gyration for the ideal freely jointed chain, you can show that that is related to the mean square end-to-end distance through this relationship, from which you can show that Rg scales as molecular weight to the 1/2, which is something that holds for ideal chains. Radius of gyration is an experimentally accessible quantity. For example, for proteins it becomes very important as biological macromolecules. It is typically measured using techniques like small angle X-ray scattering or small angle neutron scattering. When you look up sizes in 3D and when you start thinking of polymers in 3D, especially in the presence of solvents, another term that you would come across very often in the literature or when you read papers or in textbooks is this idea called hydrodynamic radius, which is a related concept but not the same as radius of gyration. Hydrodynamic radius, given as R sub h, is defined as the radius of an equivalent hard sphere diffusing at the same rate as the polymer. Now, if you consider the polymer in 3D and if you can approximate it as a hard sphere and if you can describe that with a specific radius in the solvated state, then that radius for that hard sphere in the solvated state diffusing as the same rate as the polymer would be the hydrodynamic radius. So, it gives you information about the apparent size adopted by the solvated and diffusing molecule. And it turns out that Rg and Rh give you what you would call complementary information. And Rh can be obtained from light scattering experiments using the Stokes-Einstein equation. If you are not familiar with this, I would suggest that you look it up and see how this can be used from an experimental perspective, what parameters are needed, what inputs are needed to go into this equation for you to be able to determine hydrodynamic radius. So, as it turns out, Rg and Rh give you complementary information about the size of a macromolecule. Rg tells you something about the compactness of the macromolecule and gives you information about the spatial distribution of the mass within the macromolecule itself, whereas Rh gives you information about diffusion and solvation, as we have just seen. And it turns out that Rg over Rh is a very important factor which can tell you something about the shape of macromolecules based on what that ratio is. This is true especially for proteins. For example, If Rg over Rh is 0.775, these would be considered compact spheres, whereas if Rg over Rh turns out to be 1.5, they would be random coils. So, now going from shape, you can going from size, you can now use that information to say something about the shape of the macromolecule in 3D. Now, that is a very, very important idea. What we have done in this lecture so far is we have given what I would call scaling laws, although we have not gone into the derivations of each of them. If you are interested in polymer physics, you are interested in understanding the derivations of some of these, I would suggest that you can look up this particular textbook. And many of the scaling laws that we have today have come to us from this person called Degennes, who was a French scientist who won the Nobel Prize in Physics in 1991 for his contributions to polymer physics. Our goal here has largely been to understand these things not for the purpose of understanding polymer physics per se, but to use this as a base to see how to contextualize these structure property relationships for function and performance later. So, that is why if you see, we have been primarily focusing on a physical understanding of some of these ideas. Now, if you want to put it all together, what we want to say in ending this lecture is to appreciate the fact that single chain properties can have very far reaching effects on bulk properties at the macroscopic scale. And I have given you several examples of that here just to sort of get you excited about why single chain properties are important. As we have seen, single chain properties affect both solution and melt states. We saw that you can actually have extended or expanded chains, real chains with a different scaling exponent in a good solvent as compared to a collapsed chain in a poor solvent. And later on, when we look at solvent effects, we will talk about something called an expansion factor that can quantify this in relation to the ideal chain itself. So, that becomes important for how polymers behave in solutions and in the melt, and that can in turn have consequences for processability, for example. Chain dynamics can also be used to obtain weight average molar mass, and I said earlier that you can get weight average molar mass through light scattering experiments. So, I will leave it to you to see if you can make a connection between the two. We have also seen in this lecture that chain properties can affect the relative stiffness or rigidity or flexibility of polymers, and that in turn can have far reaching consequences for bulk macroscopic properties. Chain properties can influence swelling and cross linking of hydrogels, right. We will see later in the context of cross linked hydrogels how swelling behavior is influenced by some of the ideas that we have seen so far. And again, single chain properties can influence other bulk properties such as crystallinity and glass transition, some of which we will look at in later lectures, and also other bulk behavior like viscoelasticity and more specifically creep and relaxation. So, in one slide what we are trying to summarize here or to highlight here is that single chain properties, while it may seem that one can ask why should we care about it, the real answer is that is an excellent starting point for us to understand how polymers can organize or how these single chain dynamics can help us extrapolate and draw conclusions about bulk macroscopic behavior. That structure property paradigm that I have just described is something that will recur throughout this course.